Imagine, if you will, a world without airports. A world where the only way to cross an ocean was to pack yourself on top of a controlled, continuous explosion. That's a bit like our relationship with space today. We rely on rockets, these magnificent, noisy, and frankly rather risky beasts, to punch their way through our atmosphere. But what if there was another way? What if we could simply ride? This isn't some far-fetched science fiction dream, but a concept grounded in real physics. It's called a space elevator. It's a ribbon, a tether, a cosmic highway stretching from the ground right up into the blackness of space. It's an idea that could fundamentally rewrite our future as a species. The concept itself is elegantly simple, even if the engineering is mind-bogglingly complex. Think of it as a vertical railway line. At the bottom, an anchor station, perhaps floating on a platform in the Pacific Ocean, right on the equator. From this station, a super-strong cable, a mere ribbon of material, stretches upwards. It goes up and up, past the clouds, past the International Space Station, all the way to a point some 35,786 kilometers above the surface. This is geostationary orbit, the magic altitude where an object orbits the Earth at the same speed the planet spins. And to keep the whole thing taut, a counterweight sits even further out. A captured asteroid, perhaps, pulling the ribbon tight like a guitar string. So instead of the violent, fiery drama of a rocket launch, picture this. You walk into a comfortable cabin called a climber. It looks a bit like a high-speed train carriage. You find your seat, buckle in, and look out the window. There's a gentle hum as powerful electromagnetic motors engage with the ribbon. With a smooth, inexorable acceleration, you begin to ascend. The blue skies of Earth slowly give way to the deep velvet black of space, a journey not of minutes, but of days. This isn't about brute force anymore. It's about a persistent, steady climb up a ladder to the heavens, a celestial commute that could change absolutely everything about our place in the universe. This grand structure would be more than just a new way to get to orbit. It would be a permanent bridge between our world and the next. It represents a shift in thinking, from visiting space to inhabiting it. Rockets are for expeditions, brief and expensive forays into the unknown. A space elevator is for commuters, for cargo, for industry, for families. It's the difference between chartering a tiny boat to cross a raging sea and building a grand suspension bridge. One is an adventure for the few. The other is a highway for the many, opening up a continent of possibilities that were previously just a distant dream. So how does this magnificent structure actually work? The science is a beautiful dance of gravity and momentum. It all hinges on a special place in the sky called geostationary orbit, or GEO. At this specific altitude, about 35,786 kilometers up, the time it takes for a satellite to circle the Earth is exactly 24 hours. Since the Earth also takes 24 hours to spin on its axis, a satellite in GEO appears to hang motionless over one spot on the equator. This is the sweet spot. The space elevator's ribbon would be attached to a massive counterweight, maybe a hefty asteroid we've nudged into place, orbiting far beyond GEO. This counterweight is constantly trying to fly away from Earth, pulling the ribbon taut. The real magic, the secret sauce, is the material for the ribbon. For decades, this was the biggest roadblock. We needed something with unimaginable tensile strength, the ability to withstand immense pulling forces, while also being incredibly lightweight. Steel, titanium, even Kevlar wouldn't come close. They would snap under their own weight long before reaching orbit. But then came the discovery of carbon nanotubes and, more recently, graphene. They are pound for pound, hundreds of times stronger than steel. Let's talk numbers, because that's where the story gets truly spectacular. Right now, sending 1 kilogram of anything into low Earth orbit costs thousands of dollars. Sending it to the much higher geostationary orbit costs tens of thousands. A mature space elevator system could slash that cost dramatically. Early estimates suggest the price could fall to just a few $100s per kilogram, and eventually, perhaps, even lower. This is not just an incremental improvement, it's a complete paradigm shift. With a cheap and reliable highway to the heavens, a host of new industries would spring into existence almost overnight. The most immediate and obvious would be space tourism. But this wouldn't be the current version, where just a handful of the ultra-wealthy pay millions for a few minutes of weightlessness. Nope, this would be tourism for the masses. Beyond tourism, a revolution in manufacturing would begin. There are certain processes that work much better in a microgravity environment. Growing perfect, flawless protein crystals for developing new medicines is one example. One of the most ambitious ideas is space-based solar power. This involves building gigantic solar panel arrays in orbit, where the sun shines 24/7, unobscured by clouds or atmosphere. These arrays would collect vast amounts of solar energy and beam it wirelessly down to receiving stations on Earth. For all its incredible promise, a space elevator is not without its risks. The sheer scale of the project makes it a monumental engineering challenge, and its permanent, static nature makes it a potential target. A primary concern is security. In a world with political instability and terrorism, a structure of such immense value and symbolic importance would be a tempting target. Then there is the threat from above and below. The ribbon would have to withstand the constant bombardment of micrometeoroids and the growing problem of space debris. The nightmare scenario, of course, is a complete severance of the ribbon. What would happen? Fortunately, it wouldn't be as apocalyptic as it sounds. The ribbon is under tension, not compression. If it were to break near the bottom, the upper portion, pulled by the counterweight, would simply float upwards and away into a higher orbit. If it were to break near the top, the lower portion would lose its upward tug and begin to wrap itself around the Earth along the equator. Beyond the physical risks, there are political ones. The elevator would have to be an international project requiring unprecedented cooperation, but who leads it, who pays for it? So, let's return to today, August 3rd, 2025, and imagine the elevator is a reality. How would your life change? Perhaps you are an engineer, planning your 5-year work rotation at the GEO Station shipyard, assembling the first manned vessel to Jupiter. Or maybe you're a teacher, booking a week-long school trip to a low-orbit science module to teach your students about meteorology by flying right through the clouds. The very concept of a career, of a home, would expand. People could live in vast, rotating habitats in space, O'Neill cylinders where entire towns exist in permanent comfort, with gravity simulated by spin. The solar system would cease to be a collection of distant lights in the sky, and would become a landscape of destinations, of resources, of new places to live and work. Humanity would undergo a fundamental transition from a terrestrial species to a truly solar one. So, as you look up at the sky tonight, imagine it. Imagine a thin, shimmering line ascending from the horizon, disappearing into the pinpricks of the stars. It's a ladder to a new era, a permanent connection between our world and the vast, unexplored universe beyond. It's a future of boundless potential, waiting for us at the top of a long, steady climb. The only question that remains is not whether we should build it, but what kind of future we will choose to create for ourselves when we finally arrive. What would you do if you could simply take a ride to the stars?